So if we have friction, how many fingers do we need? Just three-dimensional case. Well, we have 5, right? So if I break a finger, I only have 4. Can I still grab an object? Yeah, I think so. 4 seems to be enough. What about 3? 3. Right? So you've seen baseball pitchers, right? 3-finger. Okay. So I wasn't going to throw it at you. So let's look at the friction case now. Okay. So let's start by looking at the planar case first, and then look at the spatial case. Okay. So grasps with friction. Okay. I need more chalk, otherwise I'm going to be writing with my fingernail. Okay. Let's do an example. Okay. So let's start with let's start with a similar example. So let's have a rectangle. Okay. This time I have 2 point contacts, but now they have friction. There's friction here. Okay. So remember last time, we're sophisticated now, so we're going to represent friction in terms of friction cones. Okay, so these are my friction cones. Okay, and the angle is going to be 2 alpha. Okay, so we have 2 point contacts with friction. Okay, the left and the right. Okay, so let's call this dimension, let's call it 2r, 2 times r. All right. What do we do here? Let's do it again. Let's do exactly what we did before. Okay, and apply it to this problem. Okay, so now we have to think about what kind of forces can we generate here and here. Okay, so now because there's friction, we can apply friction in directions that are, okay, not normal. Okay, so we can apply forces anywhere inside this cone. Correct? If we go outside the cone, it slips. Okay. But as long as it's inside the cone, it's OK. So we now have more forces, directions in which we can apply forces. Okay. All right, so let's draw that again. So we have okay, so that means we can apply forces anywhere inside this cone, like that, and also over here. Okay, so let's call this f sub a, call this f sub b. Okay. How can we write f sub a? Well, we know f sub a is in the interior of this cone. So if we knew what these directions were, let's call this E1, E2, E3, and E4. Okay. Then we can say that f sub a is going to be, right, x1 times E1 plus x2 times E2. Okay, and f sub b is x3 times e3 plus x4 times e4. Okay, and maybe to indicate that these are vectors, let's maybe put arrows over the f's and e's. Okay, so f vector, vector, vector. Okay, and as before, the x's are greater than or equal to 0. Okay. Okay, so x1, oops, x2, x3, x4 are all greater than or equal to 0. Why? Because we can only push. No pulling is allowed. It'd be nice if we could write these direction vectors, okay, in some more precise way. Well, so let's think about E1. What is E1? Well, let's see. E1 points in this direction. So if we draw this, let's use a different color. Okay, so if we draw this triangle here, okay, so E1 is this plus this. Okay, this angle is alpha. Okay, half the friction cone angle. Okay. So if this length is, say, 1, then this length should be, right, so the tangent here. Okay, so recall mu equals tangent of alpha. Okay, so E1 is going to be that. Okay, because mu equals tangent alpha, so simple trigonometry. And so that means E2 is going to be 1 minus mu. E3 is minus 1 minus mu. E4 is minus 1 mu. Okay? All right, so so you see where we're going now. You see where we're going? Static equilibrium next. Okay, static equilibrium. Okay, sum of the forces equals 0, sum of the moments equals 0. So FA plus FB plus F external equals 0. Okay, and the moments. So the moment, let's just write this way, MA plus MB plus M external equals 0. Okay, this is a scalar equation because this is a planar problem. Okay, so if we write down matrix form, we're going to have x1, x2, x3, x4 here. Okay. Now over here we're going to have 1 mu, 1 minus mu, minus 1 minus mu, minus 1 mu. And then now the moments. Okay. So remember we picked our reference frame in the middle here. Okay, so the moment generated by the FA, well, there's the E1, force in the E1 direction, force in the E2 direction. Okay, so the F1, the E1 direction is going to generate a clockwise rotation, so it's going to be minus here, so it's probably minus mu r. E2 is going to be positive mu r. E3 is minus mu r. E4 is positive mu r. Okay, so this has to equal external force in the x component, negative of the external force in the y, negative of the external moment. Okay, so I'll just call this B1, B2, B3. It's the same thing as for the frictionless case, right? We're now down to the same equation. Okay, so all we have to do is ask, does there exist a positive or non-negative solution x that satisfies this equation for any b? Okay, all right, so we know how to answer that question. What do? Right, we just check to see if this, if the convex hull of the columns contains the an open ball centered at the origin, okay, in its interior. Okay. So it's really the same thing, same test. Okay, so use the Okay, so for this, and the points are maybe a little bit harder to draw. So what do you think? Is 2 fingers enough? Seems so, right? 2 fingers is enough. 2 fingers with friction should be enough for the planar case. There's actually a very nice result. Okay, that actually, for the 2-finger case, for the point contact with friction case, answers this question in a very geometric way, just by a simple drawing. Okay, so I'm going to tell you what that is. Okay, people in the business call it Nguyen's theorem because it was first discovered by a guy named Van Duck Nguyen. He was a graduate student at the time. So here's what he found. I'll just illustrate with a picture. Let's say you have a planar object. You have 2 point contacts with friction. Friction cone here, friction cone there. Okay, so Nguyen said that if you connect these 2 contact points, okay, and this line is inside both friction cones, then you have force closure in this case. Not form closure, but force closure. Okay, so that's a very, very nice result. So for a planar object, okay, constrained by 2 point contacts with friction, okay. Following horns. Force closure, okay, implies, and also is implied by, it's necessary and sufficient if and only if. Okay, the line segment, line connecting the 2 contacts, okay, lies inside both friction cones. Okay, so you don't have to do this. You don't have to draw this tetrahedron and see if the origin lies in the interior. Okay? It's quite rather simple. Okay? Now, why is this true? Okay. Not hard. Okay. Okay, so an informal proof. You can sort of fill in the details. Okay, so consider the following case. So, without loss of generality, say that's the object. Okay, let's say we have, I don't know, something like that. So we have these cones here and here. Okay, all right, so pick a reference frame. Let's choose it so that the x direction is this way, the y direction is along the line connecting the two contact points. Okay, and then we can call this angle theta 1, theta 2, theta 3, theta 4. Okay, so we have 4 directions. Okay, so the directions are, okay, so with x and y defined in this way, this will be sine theta 1, cosine theta 1. Okay, this vector will be minus sine theta 1, sorry. Minus. Okay, so this will be sine theta 2, cosine theta 2. This direction will be sine theta 3 minus cosine theta 3. Okay, finally we have minus sine theta 4 minus cosine theta 4. Okay, so we have these 4 directions. And now if we write the static equilibrium equations, okay, like we did before, okay, so force is going to be x1 times this direction plus x2 times this direction, okay, inside here. Okay, so ultimately we're going to get an equation minus sine theta 1, cosine theta 1. And over here, if you calculate the moment, I think this should be minus sine theta 1. Okay, and then you write E2, E3, E4. Okay, so this is sine. Is that right? Yeah, okay. And then sine theta 3 minus cosine theta 3. And this will be, I believe, a minus sine theta 3. Okay, and then finally we have minus sine theta 4 minus cosine theta 4 minus sine theta 4. Okay, so this times x1, x2, x3, x4. So, well, all right, I'm assuming that the distance here is just 1 here. Okay, so this is 1, this is 1. Okay, let me 1, 1. Okay, so that has to equal some arbitrary b1, b2, b3. Okay, so if you just look at this case, you'll see that this is a case where it works. Okay, so just check the convex hull formed by these 4 columns. Okay, and you should verify that this case works, has a solution. Okay, let's clean this up a little bit. Okay, now how many other cases are there? Okay, so that's case 1. Case 2, we have, okay, so let's just draw the context now. We could have something like that. Okay, could be inside one but not the other. So you have to check that. Case 3, we could have, okay, okay, could have that. And if you want to be really thorough, okay, you might want to differentiate this into two different subcases. You have that. Okay, so these are all. So these are all the possible cases. Okay, so you just work it through. Work it through. You'll see that you don't have foreclosure for case 4, case 3, case 2. Only case 1 satisfies forced closure. Okay, so that's kind of an informal description of how to prove Yuan's result. Okay. All right. So let's stop here. And if you have questions about the material today, the discussion section this afternoon will be a good chance for you to ask. Okay, thank you.